Greetings. This is part 2 of module 2, Engineering Properties of Rocks. In the first part, we have seen how rocks are used in civil engineering field and what are the requirements for rocks to be used in such civil engineering fields. In that, we have seen rocks are primarily used in three areas in civil engineering field. One at sites for foundation purposes, second as building stone or stone for construction, third as aggregate in highways and concrete. In that we have seen uniaxial compressive strength, tensile strength, shear strength and modulus of elasticity for foundation purposes, and in rocks used as building stone or stone for construction we have seen crushing strength, transfer strength and porosity. In this video we will start from durability. So density, this we have already seen in the physical properties of minerals. It is a physical property. It is how heavy it feels. Density is mass per unit volume. Units are gram per cubic meter, cubic centimeter, or kilogram per meter cube, or kilonewton per meter cube. So once you know the mass and the volume of a rock, you can easily find density. Finding mass is very easy. You can use a weighing scale to determine its mass. Finding volume is little difficult. If you have a measuring jar, you can take water in it and you note down the initial volume of water occupied, and when you drop a rock in it, the volume of water rises. So the final and initial, the difference between final and initial volume will give the volume of rock. But if you don't have a measuring jar, and you can also calculate the volume. So you take a container having water, you drop a rock into it and collect the displaced water. Once the weight of the displaced water are known, you can easily calculate the volume of the water. The volume of water is nothing but volume of displaced water is nothing but the volume of rock. So once you know the mass and volume, you can easily find density. So in civil engineering applications, greater the density, greater the use of the rock. The porosity of the rock is indirectly found using the absorption value test. This is the capacity of a stone to absorb moisture when immersed in water for 72 hours or till saturation. Absorption value is saturated weight minus dry weight divided by initial dry weight, and in percentage, for percentage it is multiplied with 100. For a good stone, the percentage absorption by weight after 24 hours should not exceed 0.6%. Rocks with greater absorption values are undesirable as building stones because the presence of water not only makes rocks weak but also makes them susceptible to frost action, chemical decay, etc. Therefore, some sandstones, limestones, etc. which show absorption values greater than 10% are considered unsuitable as building stones, particularly under moist conditions. As we have seen, compared to igneous and metamorphic rocks, sandstones have high porosities. So sedimentary rocks have high porosities. So those sedimentary rocks cannot be used as building stones, particularly when moist conditions. Durability. Durability is a very important requirement of a good building stone from the civil engineering point of view because it refers to the life of the construction made. It is determined using soundness test. The durability of a stone can be determined by subjecting the stone samples to the weathering action of sodium sulfate. The test specimens of 5 cm side cubes are dried completely and weighed. Then they are suspended in 14% solution of sodium sulfate decahydrate for 4 hours at 29 degrees Celsius and then air dried. Once it is air dried, it is oven dried at 150 degrees Celsius. This makes one cycle. After subjecting the stone sample in 30 such cycles, the loss of weight is determined. This gives the measure of the durability of the stone tested. Normally, the loss of weight should be lesser for good durability point of view. The next value is abrasive resistance test. This test is done to find out the rate of wear of stones which are used in road construction. The result of the test, it is also for building stone also the same test. The result of the test indicates the resisting power of stones against the grinding action under traffic. So when the load is applied on the stone, the aggregate, the particles, there is attrition between the particles which results in the weathering. So this is tested using abrasive resistance test. Sample of stones is broken into pieces of about 60 mm size. Such pieces weighing 5 kg are put in both the cylinders of devil attrition testing machine. It is the devil testing machine is shown in the figure. Such pieces weighing 5 kg are put in both the cylinders as I mentioned. The cylinders are closed. Their axes make an angle of 30 degree with the horizontal. Cylinders are rotated above the horizontal axis for 5 hours at the rate of 30 rotation per minute. After this period, the contents are taken out from the cylinders and they are passed through a sieve of 1.5 mm mesh. Quality of material which is retained on the sieve is weighed. Percentage wear is worked out as follows. Loss in weight to the initial weight. For a good quality rock, the percentage wear should be less than 3%. Next, appearance. It is one of the most important parameter of rock to be used as a building stone. Stones which are to be used for face work should be decent in appearance and they should be capable of preserving their color uniformly for a long time. Light colors will be pleasing. Further, they should be capable of taking a high degree of polish and retaining the same. A good building stone be of uniform color and free from clay, cavities, holes, spots of other colors, bands, etc. So it should be very light in color, and once you do any polishing on its surface, it should retain the polishing for a long time, and it should be free from any cavities, holes and other colors. Frost resistance. Under weathering, we have learnt about the natural disintegration of rocks due to frost action as frost wedging and frost heaving happens. Resistance of a rock to frost action obviously depends mainly on its porosity, because only porous rocks give scope for percolation and trapping of water. Once the water is trapped inside, under suitable conditions, it can form into ice. So once the ice is formed, the volume of ice is larger than the volume of water. So it creates a wedging action in the rock, causing disintegration of rocks. Therefore, rocks with negligible porosity like granites and quartzites have greater frost resistance, and some sandstones and limestones which are porous possess lesser frost resistance. Frost action is effective in cold and humid regions. So in such areas, massive, impervious and hard rocks should be preferably used. Fire resistance. The fire resistance of rocks become necessarily particular when they are used near places like clints and furnaces. When the rocks are used in the construction of chimneys, clints and furnaces, the temperature of the structures will be very large, where the temperature prevailing may be 850 degrees Celsius or more. The fire resistance of a rock will be more if it expands or contracts uniformly throughout its body. Mainly it depends upon two criteria: mineral composition and grain size. Monomineralic rocks like quartzites, marbles, compact limestones and dolomites undergo uniform expansion or contraction by virtue of their abundant presence of a single mineral or material in their body. So their mineral composition should be made up of only one mineral. But rocks like granites, which are coarse-grained and comprise different minerals as essential minerals, suffer unequal expansion or contraction within their body. Hence they crumble easily, particularly when subjected to quick and alternating changes in temperature conditions. So if the mineral compositions, if only one or two minerals combine together to form a rock, those minerals are very resistant to fire. But if a rock is combined of many minerals, it undergoes varying degrees of contraction or expansion, resulting in the disintegration of the material. Similarly, when the grain size of the rock are very small, when it is finer, it undergoes least volume of expansion, whereas coarse grain undergoes large volume of expansion. So finer grain size of rocks having finer grain size resists fire to a greater extent. Hardness. It is very similar to abrasive resistance test. Instead of rotating the drum with the aggregate, here we are putting steel balls inside it to find out how hardness the rocks are. The Los Angeles abrasion testing mission is shown in the figure. So here you take the aggregates and you place the steel balls inside the aggregate inside the drum of Los Angeles abrasion testing mission, and you start rotating. Upon particular rotation of the drum, we take out the sample and sieve it through 1.7 mm sieve, and we will find the percentage of fines as the total weight of the sample. If the percentage of fines is lesser, the rock has higher hardness. A maximum value of 40% is allowed for waterborne macadam base course in Indian conditions. For bituminous concrete, a maximum value of 35% of fines is specified. Impact resistance. The aggregate impact test is carried out to evaluate the resistance to impact of aggregates. Aggregates passing 12.5 mm sieve and retained on 10 mm sieve is filled in a cylindrical steel cup of internal diameter 10.2 mm and depth 5 cm. The material is filled in 3 layers where each layer is tampered for 25 number of blows. Metal hammer of weight 14 kg is arranged to drop with a free fall of 38 cm. 50 number of blows are given. The crushed aggregate is allowed to pass through 2.36 mmc, and similar to Los Angeles abrasion test, the percentage of fines are calculated, and percentage of fines less than 50% are recommended. For bituminous macadam, and maximum permissible value is 35%, and for waterborne macadam the maximum permissible value is 40%. It should not exceed 40%. So the next property is binding property. It is necessary that road stones should possess a good affinity for binding materials to ensure stability. Stones which have the ability to form their own binding material under traffic are undesirable. This property is tested as follows. From a finely ground paste of the test specimen, small briquettes are made. Small briquettes means cylinders, compressed cylinders. After drying, these briquettes are tested by a standard hammer. The number of blows required to break the briquette gives the approximate measure of the binding value of the road stone. In this way, the binding power is described as low if the briquette breaks before 10 or less blows, and fair if it withstands 10 to 25 blows, and good up to 75 blows, and very good if it resists 100 blows or more. Hydrophobic properties. Hydro means water, phobic means fear. So for a good rock, it should repel water. When the road aggregates have bitumen as the binding material, the shear strength of the mix largely depends on the degree of cohesion achieved by the bitumen layer in between the aggregate material. This cohesion is lost in some cases where these aggregates are constantly exposed to water. The cause for this loss of cohesion is the affinity of the aggregates for water, whereby the bitumen is replaced by the corresponding film of water. Such type of aggregates which have a good affinity for water are known as hydrophilic aggregates. The other type of aggregates which have marked resistance to this property of stripping of bitumen on exposure to water are called hydrophobic aggregates. So we have to use hydrophobic aggregates, water repellent aggregates. Quartzites and sandstones, being typical examples of hydrophilic aggregates, are unsuitable to be used as road aggregates. Limestone, on the other hand, is a good example of hydrophobic aggregates. The final property is cracking resistance. The superficial cracking of concrete may take place either due to clay content of the aggregate or due to the alkali reaction of the aggregate. In the first case, if the aggregate contains clay minerals, that is clay minerals of montmorillonite group, they swell on coming in contact with water, resulting in the cracking of concrete. In the second case, cracking of concrete may occur due to the reaction between alkalis in cement and reactive aggregates. As a result of this reaction, a gel is formed around the reactive mineral. This gel in turn absorbs water by the osmotic process. As a consequence of this, internal pressures develop and cracking of concrete takes place. This kind of alkali reaction becomes harmful only in the case of high alkali cements having a total alkali content of 0.6 or more. Among other undesirable constituents are iron sulfate minerals. So these are the various properties a civil engineer must perform depending upon the usage of rocks, depending upon where he is using the rocks. Thank you.